Good morning, cadets. Today we are discussing very important principle. Before we discuss the important principle, that is Bernoulli's principle, we have to conclude about the types of flows. We know that the steady flow is achieved by the flow of fluid at low speeds. When the flow of fluids are at low speeds, then that steady flow is also called as streamline flow. At low speeds, steady flow is achieved by the fluids. Now, when the speed of the fluids increases beyond a limiting value called as critical speed, then the flow will no more be steady. The flow loses its steadiness. It becomes a non-steady, unsteady, and then finally it will become a turbulent flow. So we are defining that limiting value of speed as a critical speed. So critical speed is the speed of the fluid flow beyond which it will become unsteady and turbulent, below which the flow will be still steady. So we will define what is critical speed. The maximum speed of the fluids above which the flow becomes unsteady and turbulent. Means when the flow speed crosses this critical speed, then it becomes unsteady and further it becomes turbulence. For example, you must have observed when the fast flowing fluid encounters a rock, then the fluid particles surround that rock and you will find the whirlpool like structures forming foamy structures with white water rapids. We call them as white water rapids. White water rapids are formed around the rock. When the fast flowing fluid encounters the rock, then you will find whirlpool like structures, and you will find, suppose this is a rock, and if the flow encounters this rock, you will find kind of unsteadiness, and you will find this kind of white water rapids are formed. You will find foamy like water here with whirlpool like structures. So the water whirls here, forming the white water rapids. So here it becomes turbulent. So naturally, whenever fluid is having the turbulence, then the pressure variations will be observed. Pressure will no more be constant. Pressure variations will be observed, and velocity variations will also be observed. Then the flow will no more be steady. Okay, this is how we conclude from the study of types of fluids, types of flows. That is, one, streamline flow or steady flow. Second one is unsteady, and for the turbulent flow, right? Okay. Before we go into the details of turbulence and so on, we will first learn the very important principle called as Bernoulli's principle. Fluid flow is a complex phenomenon. We shall now study the properties of streamline flow using conservation of energy. Consider there is a pipeline of this nature having its opening end and having two ends open. One is of cross sectional area A1 and the one is of cross sectional area A2. And you can see A1 is of cross section area greater than A2, as you can see, and these opening ends are at different heights H1 and H2 with respect to ground level, and there is a flow of fluid. When the flow of fluid takes place, steady flow, I can just represent the streamlines. You can see the streamlines here. I have just chosen 3 streamlines, and the spacing between the streamlines at the first end, let me call this as first end, first opening. The spacing is quite larger here compared to the spacing between the streamlines at area A2. A1 and A2 are the areas of cross sections of this pipeline, and the flow is steady flow, and we are considering incompressible fluid flow. Consider an incompressible fluid in steady flow. Across different heights H1 and H2 as shown in the diagram. Now, when the areas of cross sections are different, definitely the pressures at these different positions are also different. Let P1 be the pressure acting at area A1 and P2 be the pressure acting at area P2. P1 and P2 are the pressures acting on the fluid. Okay. As a result, the fluid can rise and come out of this area A2 at height H2. So there is a rise in the level of height. And when you look at the streamlines, there is a gain in velocity. If the velocity of fluid coming out here is taken as V2 and velocity of entry of the liquids is taken as V1, right? Then you can see V2 is greater than V1, as we have stated earlier using the equation of continuity. A1 V1 is equal to A2 V2. Since A2 is a smaller cross section area, then V2 is definitely greater than V1. This is the equation of continuity for an incompressible fluid. A1 V1 equal to A2 V2. So here A1 is greater than A2. A1 is greater than A2. This implies V2 must be greater than V1. So there is increase in velocity as it rises from H1 to H2. There is an increase in velocity. So when there is increase in velocity, we say that there is gain in kinetic energy, right? And there is increase in height of the flow of fluid also from H1 to H2. So when there is an increase in height of the flow of fluid, there is a gain in potential energy. So the question arises, at what cost there is a rise in kinetic energy and there is a gain in potential energy? There must be potential, there must be pressure difference. So the pressure difference that occurs here, P1 and P2 are of different pressures. So definitely P1 acting at A1 must be greater than P2 acting at A2. So this pressure difference P1 minus P2, P1 must be of higher pressure, P2 must be of lower pressure. So this pressure difference, got the point? P1 minus P2. this pressure difference leads to change in kinetic energy. That's what we call it as gain in kinetic energy and gain in potential energy. This relation of the pressure difference which causes the gain in kinetic energy and the gain in potential energy of an incompressible steady flow of fluid was first formulated by Bernoulli. It was first formulated by Bernoulli in 1738. Swiss scientist. He is Swiss scientist. Switzerland. His complete name is Daniel Bernoulli. So he gave the relation between the pressure difference with gain in kinetic energy and gain in potential energy. So this is strictly according to law of conservation of energy. Law of conservation of energy, right? Then we try to relate between the gain in kinetic energy and gain in potential energy at the cost of the pressure difference. Means there must be work done. Work must be done on the flow of fluid. As a result, the fluid can raise from height h1 to h2, right? And fluid can gain the velocity from v1 to v2 as it moves from the region 1 to region 2. The velocity is increasing and the height is also increasing. So as height is increasing, potential energy is increasing. As velocity is increasing, kinetic energy is increasing. So this increase in potential energy and increase in kinetic energy must be due to pressure difference. There must be work done by the pressure difference. So work done by the pressure difference must be appearing in the increase in potential energy and increase in kinetic energy. This relation was first found by the Swiss scientist Daniel Bernoulli in 1738. It has become a very important principle. Okay. Now I will write it in short. The pressure difference must be the cause of the pressure difference is related to the difference in kinetic energy and difference in potential energy. Difference in potential energy. So it is as a consequence of law of conservation of energy. Conservation of energy. So this Bernoulli's principle is based on conservation of energy, law of conservation of energy. First we calculate work done at the first region of area of cross section A1, and then we calculate work done at the area of cross section A2. So if work done here is W1 and work done here is W2, then we take the difference between the work done. So the total work done by the pressure difference W1 minus 2, W1 minus W2 must be resulting into change in potential energy and change in kinetic energy. That's how we relate work with the energy. That is what we call it as work energy theorem. So we are applying work energy theorem over here. Okay. So to calculate that, let us see the volume of water that is entering with velocity v1 here. Suppose this point is taken as P and suppose this is the point C, right? And I will draw this. Yes. In time delta t, when the fluid enters with velocity v1, it covers a length of about v1 delta t in time delta t. So we can calculate what is the volume of the fluid that is entering, right? And what is the volume of fluid that is leaving? That also we calculate, and using the equation of continuity, we know that the volume of fluid entering per second is equal to volume of fluid leaving per second. That is what we learned as volume flux remaining constant. The rate of flow of the fluid, in steady flow is always constant. So if this point we called as D and this one is taken as E, this is of area of cross section A2, okay, and the liquid that is flowing out will be of velocity v2, right? Now in the same time delta t, the liquid covers a distance d to E. Let dE be the length of the liquid covered in time delta t. So volume of the fluid entering in time delta t is equal to volume of the fluid leaving in time delta t. This is what we call as law of continuity. Using equation of continuity, volume of liquid, I have written liquid here because we are considering incompressible fluid. Incompressible fluid means whose density does not change. Even though pressure changes, the density remains same. Such a liquid is called as incompressible fluid, right? So volume of liquid entering in time delta t is equal to volume of liquid leaving in the same time delta t. So we will calculate what is the volume. So here the volume of liquid that is entering in time delta t is A1 V1 delta t, as we have calculated earlier. A1 V1 delta t equal to the volume of liquid that is leaving out in the same time delta t is V2 delta t into A2. That becomes volume. A2 into V2 delta t. These are of different cross sections, as I have told you. This is of area A1 and this is of area A2, such that A1 is greater than A2, right? A1 is greater than A2. Okay. So this volume, let us call it as delta B. Let us call it as delta capital B. Delta capital B. This is volume of liquid remaining constant according to the equation of continuity, right? Now, with the help of this one, we can now calculate what is the work done on this volume of liquid that is entering and what is the work done by this, the liquid that is coming out, same volume of liquid that is coming out. So, we will calculate now. Work done on the liquid entry at B, we will call it as W1. W1 is equal to force into displacement, but we don't know force. There must be a force acting on this so that the liquid accelerates. So we will calculate work done in terms of force into displacement. So force is calculated as pressure into area. Okay. So pressure is P1 here. let P1 be the pressure at the opening at A1. So pressure P1 into area A1 into area A1. So the distance is V1 delta T in time delta T. So that is what work done on the fluid entering at B in time delta T is calculated as P1 into A1. P1 A1 gives us the force. Pressure is equal to force by area. So force is equal to pressure into area. Pressure into area gives us force. This force multiplied by the distance covered in time delta T. Distance covered in time delta T is V1 delta T, where V1 is the velocity with which the liquid enters. Right? This is the W1. In the same way, we can calculate work done by the fluid at A2. Work done on the fluid leaving E. We call it as W2. W2 in the same way I can write pressure P2 into area A2, and the length that is covered in time delta T is V2 delta T. V2 delta T. Now the pressure here at P2 must be less than pressure here at P1, right? The pressure at B must be greater than pressure at P. So if pressure here is P1 and pressure here is P2, then P2 will be less than P1, or P1 is greater than P2. So this pressure difference P1 minus P2 leads to the work done. So we will calculate the total work done. So total work done due to pressure difference. Total work done due to pressure difference now becomes W1 minus W2, because here the work is done on the fluid and here the work is done by the fluid. Therefore, if work is done on the fluid is taken positive, work done by the fluid is taken negative. Therefore, it becomes difference in work, W1 minus W2. I think you got the point. So P1 A1 B1 delta T is positive and P2 A2 B2 delta T becomes negative. Therefore, I will write P1 A1 B1 delta T minus P2 A2 B2 delta T. So instead of writing again and again A1 B1 delta T, A2 B2 delta T, we know that A1 B1 B2 A1 B1 delta T, A2 B2 delta T is taken as the volume of fluid entering, which is equal to volume of fluid leaving. So we can write it as just delta B. So take the difference P1 minus P2. So you can write this entire A1 B1 delta T as delta B, because we know that delta B is equal to A1 B1 delta T, which is also equal to A2 B2 delta T, which is same volume. Volume flux remaining constant. That is applying equation of continuity. Therefore, P1 minus P2 delta T. I think you understood how P2 becomes negative. Here, P1 is work done on the fluid, which is positive. P2 is the work done by the fluid. So, work done by the fluid is taken negative. Okay. Therefore, when the work done by the fluid is taken negative, then W2 becomes negative. When W2 becomes negative, then total work done becomes W1 minus W2. W1 minus W2 is equal to W1 minus W2 becomes P1 minus P2 into delta B. P1 minus P2 into delta B. Right. Now, using the work energy theorem, we can relate this change in work done or work done on the fluid equal to gain in kinetic energy and gain in potential energy. Now we will first calculate what is gain in kinetic energy. Gain in kinetic energy of the fluid. So this I can write it as delta K, delta capital K, half delta M into V2 square minus V1 square. That's how we call it as gain. Gain means final kinetic energy minus initial kinetic energy. Final kinetic energy is, you see here, half delta M V2 square, and initial kinetic energy is half delta M V1 square. Therefore, I have written this. You can write one sentence here about half delta M V2 square minus half delta M V1 square. So if you take the difference, you will get delta M into V2 square minus V1 square. That becomes the gain in kinetic energy. But delta M we don't know. We know the density. Let us say rho is the density of the incompressible fluid. Rho is the density of the incompressible liquid that is flowing in streamline flow, flowing in steady flow, right? So the density doesn't change. Therefore, we can write this delta M in terms of density and volume. Here, rho is equal to delta M by delta V. Therefore, delta M is equal to rho into delta V. We can substitute this in this equation. Therefore, gain in kinetic energy becomes delta K equal to half delta M is replaced by rho delta V into V2 square minus V1 square. Let us call this equation as 2 and this W1 minus W2 as equation number 1. Okay. Now gain in kinetic energy, we have got the equation. In the same way, let us write gain in potential energy. Similarly, gain in potential energy. Definitely there is a gain in potential energy since the liquid is rising from lower height H1 to greater height H2. Therefore, we can calculate gain in potential energy, that is as delta capital U. In the same way, we can write it as delta M, that is the mass of fluid entering per second, mass of fluid entering per second into G, mg H. The difference in height is H2 minus H1. Again, this is written as delta mg H2 minus delta mg H1. Final potential energy is delta mg H2. Initial potential energy is delta mg H1. So difference in potential energy becomes final potential energy minus initial potential energy. Delta mg into H2 minus H1. Now again substitute what is delta M. Delta M is rho delta V. Therefore it becomes rho delta V into G H2 minus H1. So this becomes equation number 3. So this is change in potential energy. Therefore now applying the work energy theorem. Employing work energy theorem. Work done by the pressure difference on the fluid is equal to the gain in potential energy and gain in kinetic energy. That's how left hand side will be work done on the fluid. Work done on the fluid is W1 minus W2. So W1 minus W2 I will write directly as P1 minus P2. So W1 minus W2 can be now written as P1 minus P2 into delta V, that is from equation number 1, is equal to gain in kinetic energy delta K plus delta U So from equation number 2, it is half rho delta V into V2 square minus V1 square plus rho delta V, that is gain in the potential energy, rho delta V into G H2 minus H1. So this is nothing but work done W1 minus W2 equal to change in kinetic energy plus gain in potential energy. This is what I have done completely. So you can see here delta V is here also and delta V is here also. So throughout delta V is common, so we can cancel delta V. So that now we get a simple equation. So finally we get the equation after cancelling delta V, P2 minus P1 is equal to half rho V2 minus V1, V2 square minus V1 square, because delta V cancels, plus rho G H2 minus H1. So this itself is going to be called as Bernoulli's equation. You can see here the work done per unit volume. Left hand side is work done per unit volume on the flow of fluid is equal to gain in kinetic energy per unit volume and gain in potential energy per unit volume. This is how we can write the Bernoulli's principle. So for an incompressible flow of incompressible steady flow, incompressible steady flow of fluid left hand side is work done per unit volume. Work done per unit volume. Work done per unit volume is also equal to pressure difference. Pressure difference. It is also equal to pressure difference. Work done per unit volume equals the sum of gain in kinetic energy per unit volume, gain in kinetic energy per unit volume, because volume is cancelled, per unit volume, and gain in potential energy per unit volume. So you can look at this equation. So work done per unit volume is nothing but P1 minus P2 equals sum of gain in kinetic energy per unit volume. Kinetic energy per unit volume is half rho V2 square minus V1 square, and gain in potential energy per unit volume is rho G H2 minus H1. So this is called as Bernoulli's principle, right? So this Bernoulli's principle can be still made simple way by collecting the terms, all ones one side, all twos on another side. Now let us take all ones one side. If we take P1 to the right hand side and V2, V1 and V2 and H2 on the left hand side, we can write P2 minus, P2 plus, you can write P2 minus rho V2 square minus rho G H1 rho G H2. This is all having suffixes 2 is equal to P1 on this side plus it will be P1 plus no it will be negative P1 minus half rho V1 square minus rho G H2. So this is the second way of writing the Bernoulli's principle. Okay, I will rewrite the equation once again. There is a small correction here. It is not P2 minus P1. It's wrong. Since P2 is lesser pressure, it is always P1 minus P2. In all other equations, I have written P1 minus P2. You can see here P1 minus P2. So it is P1 minus P2. So all P1s you collect at one side, all 2s you collect at the other side. So we'll get P1 and you take this side, it becomes half plus half rho V1 square plus rho G H1, right? All positives must be equal to. You take P2 on the right hand side, then we will get positive P2 plus half rho V2 square plus rho G H2. Means P1 rho V1 and H1, they are all related to the end 1. P2 A2 H2 V2, P2 A2 H2 V2 are all related to end B, end second end. That is, this is the second end. So as the fluid flows from first end to second end, pressure varies from P1 to P2. The kinetic increases from half rho V1 square to half rho V2 square per unit volume, and potential energy per unit volume also increases from rho G H1 to rho G H2. So in this way we can write in general when the incompressible flow of fluid takes place across a pipe of varying pressures, varying cross-section areas and varying pressures, then the sum of pressure, kinetic energy per unit volume and the potential energy per unit volume, it remains always constant. So this is another way of writing Bernoulli's principle. So you can write it once again. For an incompressible steady flow of fluid, the sum of pressure, kinetic energy per unit volume and potential energy per unit volume remains always constant for an incompressible steady flow of fluid, right? So this is strictly in accordance with law of conservation of energy. Okay, the law doesn't hold good for turbulent flow, and the law doesn't hold good for fluid which is compressible, like gases. Gases are highly compressible. So for such compressible fluids and turbulent flow, this law is not applicable. So Bernoulli's principle doesn't hold good for compressible and unsteady or turbulent flow. It is applicable only for incompressible flow such as liquid, where density remains constant, and it should be compulsorily steady flow. Then only this equation is applicable. But it has got a number of applications which we are going to study one by one later. Okay, I think you got the derivation correct. If you have any doubts, you can ask me the doubts in the video, okay, in the WhatsApp group. Thank you. Have a nice day.